Welcome to Section 7.1, Sampling Plans and Experimental Designs. In this section, we'll explore how data is collected, not just where it comes from, but how it's gathered. We'll learn that the reliability of any statistical conclusion depends not just on math, but on the design. Whether you're conducting a campus survey, planning a research study, or trying to make inferences about the population of Earth from a few dozen Marvel heroes, the key to sound inference is how you sample. Why does the sampling plan matter so much? Because it determines whether the data we collect is meaningful or misleading. Think of it like cooking. Even if your recipe is perfect, bad ingredients ruin the dish. Likewise, poor sampling introduces bias, a systematic deviation from the truth. For example, if you only survey students in the cafeteria at 11 a.m., you're probably missing commuters or those with off-campus jobs. That's sampling bias. We need to design our data collection to reflect the population accurately, not just the most convenient or vocal participants. A simple random sample gives every possible group of individuals the same chance of being selected. It's the statistical gold standard. Imagine writing the names of all 100 students in your class on slips of paper, putting them in a bowl, and pulling out 10. That's simple random sampling, or SRS. Simple random sampling helps eliminate selection bias and is great for small, well-defined populations. Tools like random number generators and Excel's RAND function make it practical even at larger scales. It's what Shield might use to choose random agents for training. Everyone has the same chance of being picked, even if some of them are, say, less enthusiastic about leg day. It's crucial to distinguish between observational studies and experiments. In an observational study, researchers don't interfere. They simply observe what already happens. Think surveys, interviews, or watching how long students stay in the library. In contrast, experiments assign treatments like giving one group of students a study aid and another group a placebo, and then measure the effects. Only experiments with random assignment allow us to infer cause and effect. We can observe this with a Marvel example. Observing Tony Stark's sleep patterns and productivity is observational. Randomly assigning Stark and Banner to two different sleep schedules and comparing performance, that would be an experiment. Even with the best intentions, sampling can go wrong. Non-response happens when people don't reply. If mostly motivated students answer a satisfaction survey, then you're missing key voices. Undercoverage happens when certain groups are unintentionally excluded. For example, surveying only students on campus would exclude commuters. Wording bias, well, that refers to the fact that how you ask questions matter. Do you agree with the disastrous decision to extend the semester? Well, that's biased wording. These issues distort the data and can be more damaging than small sample sizes. Let's say a chemist wants to test two analysis methods. She has 10 identical samples and randomly assigns 5 to each method. Why not just choose the first 5? Because there might be an unintended pattern. Maybe the first 5 were collected earlier and degraded. Random assignment ensures fairness. It balances both known and unknown factors, helping us isolate the treatment effect. Think of it like testing Captain America's shield against 2 different metals. We'd want random assignment to be sure the results aren't just due to temperature, wear, or the way it's thrown. In stratified sampling, we divide the population into subgroups or strata, such as academic major or class standing, and randomly sample from each of those groups. This method ensures representation across key categories. For instance, if you're studying opinions across class years and seniors make up only 10% of the population, stratifying ensures they're not drowned out. It's like building a superhero team and making sure you include members with different powers, not just 5 versions of Iron Man. In cluster sampling, we divide the population into naturally occurring groups, like dorms, classes, or neighborhoods, and then randomly select entire clusters. It's efficient, especially when it's hard to get a full list of individuals. For example, if you want to study classroom behavior, randomly choosing a few entire classes makes more sense than selecting students from across campus. Another Marvel example, instead of sampling Avengers across the galaxy, Nick Fury randomly selects entire SHIELD units for an audit. In systematic sampling, we select every kth person from a list. For example, every 10th customer who enters the student union. We start by randomly picking a number between 1 and k, and then we follow the system. It's quick and easy, but can introduce bias if there's a hidden pattern on the list. Imagine selecting every 10th seat in a lecture hall that alternates by major. You may skew your sample. Sometimes we can't use random methods, but non-random sampling has serious limitations. Convenience sampling is just asking whoever's nearby. It's fast, but it's not representative. Judgment sampling is where the researcher handpicks typical participants, and that can be risky. Quota sampling is where we fill quotas based on demographics, but without random selection. These methods can be useful for exploratory research or low-stakes insights, but we can't generalize the results. Randomness isn't just a statistical detail, it's the backbone of inference. Random samples allow us to apply probability to our estimates, to build confidence intervals and test hypotheses. Without randomness, our conclusions may be descriptive, but not generalizable. So if you want your conclusions to go beyond your sample, whether you're predicting campus trends or comparing training regimens for new recruits, random selection is your superpower. So to summarize, the way we collect data, our sampling design, deeply affects our conclusions. Random sampling methods like simple random sampling, stratified sampling, cluster sampling, and systematic sampling help reduce bias. Non-random methods are sometimes necessary, but come with caution. Always ask, can this sampling plan support the claims being made? Understanding sampling isn't just academic, it's how we build reliable knowledge, whether for science, surveys, or strategic decisions in any universe.